Video, we're going to start talking about rate laws. And what a rate law represents is the relationship between the concentration of each reactant in our balanced equation and the reaction rate. So it states the relationship between the concentration of each reactant in the reaction and the reaction rate. Another way to say that is that it states the dependence of the reaction rate on the concentration of the reactants. Some reactants are going to affect our rate. Some reactants actually don't affect the rate. Some affect the rate more than others. So it states the dependence sorry here, like my handwriting isn't bad enough, states the dependence of the reaction rate on concentration. And it's concentration of reactant. Rate laws are always expressed in terms of reactants and not products. When we're writing rate expressions, we include both reactants and products, right? We put negative signs in front of our reactants, positives in front of our products, because reactants disappear and products appear. Rate laws are only in terms of reactants. Products are not included in our rate laws. We can actually write that now. I'll say that again later, but product concentrations are not part of the rate law. So the general form for a rate law and let's just use a generic reaction. So let's have A moles of A. So lowercase a is representing some coefficient plus B moles of B going to, and we could just say products if we wanted, because products aren't going to be included. I was going to do C, but honestly, it doesn't really matter. And then our rate law, its general form, so the form is down here, that's actually a reaction, is going to be the word rate, an equal sign, a lowercase k. It's really important that it's lowercase. A capital K is actually going to represent equilibrium constants, which we're going to see in the next couple chapters. So do be careful. Lowercase k's are rate constants. Capital K's represent something else. So please make sure it's lowercase. I do mark off if you use the wrong symbol for your constant. So rate, an equal sign, a lowercase k. So every time you write a rate law for me, you're going to have that part. And then what comes next does vary depending on the reaction. So you're going to express, and I'm going to put both A and B in for this one. So the concentration of a reactant, remember those brackets mean molar concentration, raised to some power, and I'm going to use an X. And then the concentration of B raised to some power, and I'm going to use a Y. Both A and B might be part of the rate law for this reaction. It could be just A, it could be just B. You cannot tell by looking at the chemical equation what the rate law is going to be. It could be completely different. Not completely different, but it doesn't have to have both A and B in it. It could have one reactant, it could have both reactants. The coefficients could be 1s or 2s or 3s. They can be different for A and B. They could be the same. We don't know. The only way to determine that is to determine it experimentally, which I will write down here in a minute. I just want to define a couple of these. So lowercase k is our rate constant. And then X and Y, These are going to tell us the order of our reactants. So it tells us the order for each reactant. So if it's a 1, we would say it's a first order with respect to whatever that is. And I'll show some real examples here in a minute. If the exponent is a 2, we would say it's second order. So whatever that exponent is, that's going to tell us the order, which again, I promise I will talk more about. It's going to tell us the order for each reactant. If I was to add X and Y together, we get the overall order for our reaction. And then again, I've said this a few times, we've been using it all week, but we'll write it down. Those brackets mean molar concentration. So the concentration expressed in molarity, right? Moles per liter. So I do have a little table here with some examples. Let me get it up here so we can see it. And anytime I put a table in here, you're probably going to need to hit pause to write it down. I'm not really giving you time to do that. So please hit pause, write this down in your notes, and then hit play again when you're ready. So what this is representing, I have some reactions over here, and then its corresponding rate law. And the point of this is to just, 1, give you some examples, but 2, show that you can't just look at the chemical equation and then write that rate law. So if I look at the first one, I have 2 reactants, right? I have both dinitrogen pentoxide. Sorry, I have 1 reactant. I have dinitrogen pentoxide, but there's 2 of them, right? And my rate law just has the concentration, and it has an exponent of a 1. One habit that students, when they're first learning this, like to do, and this, you don't want to do this, is they'll take this 2 and then they'll put an exponent 2 there. This rate law does not have that. If you were to do that, you would be wrong. And again, you can't just look at the equation and get that. So if you're thinking to yourself, well, how would I know that 2 doesn't go there? You wouldn't. It has to be determined experimentally, and we'll do an example like that. If I look at my second one, I have 2 hydrogen peroxide and 1 iodine, and my rate law has both of them in it, right? Before I said it could have A and B, or it could just have A, just have B. They're both raised to the first power, even though one has a coefficient of 2 and the other has a coefficient of 1. Again, you can't just look at that equation and get the rate law from it. So just some examples. All do note that they all have the rate, an equal sign, and then a lowercase k. So every time you write a rate law, you're always going to have that part. What comes after it, again, is going to be determined experimentally. And let's actually write that down. Rate laws must be determined experimentally. And they're determined experimentally using the initial rate. So what you do, and again, we'll look at an example here in a minute, but you would measure the concentration, you would measure the rate of the reaction at various concentrations of reactant. So you would have, different reactant concentrations, and then you would measure the rate, and you would see how a change in concentration of a reactant affects that rate. Right? If we go back up and look at the definition, right, it states the dependence of the reaction rate on concentration. So as the concentration changes, how does it affect that rate? If you double the concentration, does the rate double? If you double the concentration, does the rate not change? If you double the concentration, does the rate go up 4 times? So how does a change in concentration affect that rate? So you would go into lab, you would change the concentration, you would measure the rate, and look to see how it's affected. So I'm just going to look more at this first rate law. I'm going to write this down here again. Our rate is equal to lowercase k and then the concentration of dinitrogen pentoxide. Note that there is an exponent of 1 here, right? We don't have to write it if it's 1, but there is a 1 there. So this would be a first order reaction, right? I had said that those exponents tell us the order. So this is first order. With respect to N2O5. It's also first order overall. Right, to get our overall order, we said we add our exponents. The only exponent I have here is a 1. So it's first order with respect to N2O5. It's also first order overall. What that means for us is that whatever I do to the concentration of dinitrogen pentoxide also happens to the rate. So if I double my concentration of N2O5, my rate is going to double. If I triple my concentration, my rate is going to triple. If I cut my concentration in 1/5, then my rate is going to be cut by 1/5 or cut by a fifth. So, or cut 5 times, whatever the proper way to say that is. So if it's first order, right, whatever we do to the concentration So whatever we do to the concentration of N2O5 is also done to the rate, the reaction rate. And I know that's kind of worded weird, but essentially, right, if the concentration of N2O5 is doubled, the rate is doubled. If the concentration of N2O5 is cut in half, the rate is cut in half. And that kind of statement is always going to be true if it's first order. So for a first order reaction, whatever you do to the concentration, the same thing happens to the rate. Increase the concentration 10 times, the rate is going to go up 10 times. If I had a rate law, and I'm just going to use A this time because I don't have an actual example for us, I'm going to put a 2 there. We would say that this is second order. Here comes my example. Let's get that out of our way till we're ready for it. Second order, because I have a 2 there with respect to A. It's also second order overall. And what that means is whatever I do to the concentration, I then have to square that to figure out what happens to the rate. So for example, if the concentration is doubled, the rate increases 4 times. The rate is going to be quadrupled. Kind of the way that I think about that is I'm going to say my rate, right, it's proportional to whatever that concentration is squared. So if I'm going to double it, I just kind of think about putting a 2 in here because I'm increasing it 2 times. 2 squared is 4, so my rate is going to go up 4 times. If the concentration of A is decreased, sorry guys, I just want to get these out of our way here. If the concentration of A is cut in half, what happens to our rate? What do you guys think? Again, I'm just thinking of my rate as being proportional. I'm going to put 1/2 in here and then I'm going to have to square that. So if I cut my concentration in half, what happens to my rate? Yeah, it's going to go down 4 times, right? The rate is cut in quarters, however you want to say that, right? 1/2 squared is 1/4. So second order, right? Basically, our rate is more sensitive to changes in concentration. Zero order, I didn't do an example of that, but if you're zero order, you can change the rate all you want, or change the concentration all you want, and it's not going to affect the rate, right? Let's actually write that down. If I have zero order, so we would say the rate is equal to K. You could put a 0 there. Sometimes you just don't even have to put it there. I'll do another example here in a little bit where something's zero order. But essentially, if you were to use our little way of calculating it, let's say our concentration is doubled. Anything to the 0 power, right, is just 1. 1 times my rate, nothing happens. There's no change. So if something is zero order, changing the concentration of that is not going to affect the rate. So changes in reactant concentration does not affect the rate. You can change, increase A's concentration 100 times, the rate is not going to change, right? 100 raised to the 0 power is 1. 1 times our rate is no change, right? So if something is zero order, changes in concentration do not affect it. And we could go on. Third order is pretty uncommon, but same idea. If I was to then double the concentration, my rate is actually going to go up 8 times because 2 raised to the 3rd power is going to be 8. So it tells us again how sensitive, right, that rate is to changes in concentration. We did say we have to determine it experimentally, so that's what this data is for. I have 2 examples for us here, so let's do our first one. So I said that we would go into lab and you would actually measure the rate at different concentrations. So in this example, there's 5 trials. In one trial, our concentration of bromide ions, that's Br minus, it's kind of hard to see, is 0.1 molar. Our concentration of bromate is 0.01 molar, and our concentration of hydrogen is 0.15. The instantaneous rate at time 0, right, our initial rate, is this. And then we change the concentrations, and we look to see how the rate changes. So what we're going to do is we're going to use this table to determine our rate law. And I'll give you the reaction here too. So determine the rate law for the following reaction given the experimental data above. And our equation, I have 5 bromide ions reacting with bromate plus 6 hydrogen ions. That's a positive charge. And we're producing 3 bromine plus 3 water. So the way that we're going to do this is we're going to look at sets of data. I'm going to find 2 trials where only the concentration of one of my reactants is changing. If only one of them is being changed, then the effect, the rate change is due to that particular species. Hopefully that made some sense. So if I look at trial 1 and 2 here, right, the concentration of bromide is not changing. So this change in rate is not being affected by bromide because I'm not changing it. If I look at my concentration of hydrogen ions, it's also not changing. Since that's not changing, my change in rate is not due to hydrogen ions because, again, I'm not changing it, right? The only thing that's changing here are these two, right? I shouldn't say these two, but is my concentration of bromate, which means my change in rate is due to bromate. So I'm going to use trial 1 and 2 to figure out my order with respect to bromate ions. And then what I'm going to do is I'm going to look and I'm saying, okay, I doubled the concentration, right? My concentration went from 0.01 to 0.02, so it was doubled. When my concentration doubled, what happens to my rate? So is that doubled? Is that tripled? Is it cut in half? What happened there? And if you can't tell, just get out your calculator, divide 4.8, right? Times 10 to the negative third. I'm dividing that by 1.2 times 10 to the negative third. And when I type that into my calculator, I get a 4. So what happened is, let's write this down here. We're going to look at trials 1 and 2, right? Only the concentration of bromate ions is changing. When the concentration is doubled, the rate increases 4 times. So if it was first order, right, if I doubled the rate, my concentration would double. Since my concentration is being doubled, the rate goes up 4 times. What is my order with respect to BrO3? Right? The other way to think about it, if it's not really obvious to you, right, it's kind of going backwards from before. So 4 is proportional to 2, and we're trying to guess what that exponent is. So what do you have to raise to to get 4 as our answer? 2, right? It is second order with respect to Br2. Meaning my exponent, BrO3, wow, I'm not doing very good today, am I, guys? Too many 2s. So second order, right? When I double the concentration, my rate goes up 4 times, which means my exponent has to be a 2, so it's second order. And again, it's second order for bromate ions because that's the only thing that's changing for those 2 trials, right? If I go back up, this isn't changing, this isn't changing. The only change is for bromate. We still have to find trials to figure out what the order is for bromide and hydrogen ions. So we'll find trials where the only thing that's changing is Br minus, and we'll find 2 trials where the only thing that's changing is my proton concentration. I don't know if I said it this time, but just like I said before, please, if you need to hit pause, which you're going to need to, I don't think anyone can really write that fast, please make sure that you hit pause if you haven't already and write down this table. I do want you to have it in your notes. You are going to have to be able to do these problems on tests and quizzes. So let's find 2 more trials. So let's look at, if I look at trial 1, and nope, I don't have anything for that one. Trial 2, yeah, that one works. So if I look at trial 2 and trial 4, right, what I'm trying to do is I'm trying to find something where the only thing that's varying is one of my reactants. So if I look at this one, my concentration of bromide ions is not changing. My concentration of bromate ions is not changing. The only change is for protons, which means any change here is due to protons. So let's go write that down. So for trials, my second example, I'm taking up more space than I anticipated. So for trials 2 and 4, only my proton ion concentration is changing. So any change in rate is due only to my proton ion concentration. So if we go up and we look, my rate, I'm gonna have so many colors here, my concentration is being doubled, right? I'm going from 0.15 to 0.30, so I'm doubling it, and my rate is not changing. So when the concentration of hydrogen ions is doubled, the rate does not change. So what is my order with respect to hydrogen ions? What do you guys think? If I change the concentration and the rate is not affected, what order is that? Yeah, good. Hopefully you guys remembered that we just talked about zero order, right? Zero order, we can change the concentration all we want and it has no effect on the rate. So for hydrogen ions, it would be raised to the 0 power. So we still have to look at bromide. So let's go back up here. Let me erase some of this mess. A more efficient way of erasing, sorry guys. Okay. So we want to find trials now where Br minus is changing and nothing else is. So let's look at trials. What do we look at? How about 1 and 3? Right, in trial 1, my concentration of bromate is 0.01. In trial 3, it's 0.01. So that's not changing. Hydrogen ions, 0.15, 0.15, but my concentration of bromide is going up by a factor of 3, right? If I was to take 0.30 and divide it by 0.10, I get 3. So I am tripling my concentration. And then if I look at my rate, it's also being tripled. And again, if you don't see that, grab your calculator, divide them. So take 3.6 times 10 to the negative third, divide it by 1.2 times 10 to the negative third, and you're gonna get 3 as your answer. So when I triple the concentration of bromide, my rate is also tripling. So let's write that down, trials 1 and 3. Only bromide ion concentration is changing. When the concentration of bromide ions is tripled, the rate is tripled. So what is my order with respect to bromide? Yeah, good. Hopefully you guys are thinking first order. If you didn't see that right away, again, you could do it this way, right? Our rate is tripled, so that's representing my rate. My concentration is tripled, so I'm going to put a 3 in there for my concentration. What exponent do I need? So what am I going to raise 3 to get 3? I'm going to raise it to the first power, so it's first order. So my concentration of bromide, I'm going to have a 1. And you don't actually have to write the 1. I'm just going to for effect. But when we put this all together into our rate law, I will get rid of it later. So let's write our rate law now, right? Because we're supposed to determine our rate law. So putting this all together, see how many more times I have to move that. It's going to be a couple yet. My rate law, remember it's always going to be the word rate. Don't forget these parts because you do lose points if you don't have the rate and the equal sign and the lowercase k because you're not actually writing the rate law if you don't include that. That's part of our rate law. And then I'm going to have the concentration, if I go up, BrO3 minus, and it doesn't matter what order you put these in. If you want to put bromide first and bromate next, second, that's fine. It doesn't really matter. as long as they're all included and they have the correct exponent. We said that this was second order, so I'm going to have an exponent of 2. I'm going to put the hydrogen ion in here for now. I'm going to rewrite it and get rid of it, but I am going to include it for now. And then Br minus, right, my bromide ions, which is raised to the first power. You don't have to put that one there. And it's perfectly acceptable to leave it this way if you want. The other way to do it, though, is if something is 0 order, it's actually more common to not include it, to just leave it out. If it's, right, changing the hydrogen ion concentration does not affect my rate at all, so there's really no reason for it to be there. So the more common way to write it is to write it this way. So this is the better way to do it. So just kind of looking at this, right? It's second order. I know we've already said this above. I just want to summarize with respect to bromate. It's first order with respect to bromide. And then what is my overall order? Because we haven't done one like this yet. Remember, we add our exponents to figure out our overall order. So I have a 2 on bromate. Br minus, bromide, has a 1. So it's third order overall. So first order with respect to bromate, first order with respect to bromide, third order overall. You could include 0 order with respect to protons, right, to hydrogen ions. I am going to add a second part to this. If we go back up to our table, which is way up here now and getting kind of messy, if you notice, I have the last trial, trial 5, we don't have the rate. So what we're going to do now that we have the rate law is we're going to determine our initial rate for trial 5. So I'm just going to copy this table and then paste it down here. Same table, I just want it closer to where we're working so we can not have to scroll up so much. So I'm going to rewrite our rate law down here so we have everything. Okay, so what we're going to do is we're going to determine the initial rate for trial 5. So essentially, we're just going to plug numbers into our equation and solve for rate. Our problem is we don't have our rate constant right now, right? If I look at the numbers that I have a concentration for bromide, so I can plug that in here. I have a concentration for bromate, so I can plug that in here. We're solving for rate, so that's unknown, but my rate constant is also unknown right now. So this is going to be a 2-step process. What we're going to need to do is use one of our other trials to solve for our rate constant. Once we have the value for our rate constant, then we can use the concentrations from trial 5 to determine my initial rate. I'm not going to need my concentrations of protons as part of this problem, right? Because that's not part of my rate law, right? Changing the concentration of hydrogen ions has no effect on my rate. It's not part of my rate law, so we don't need this column at all for this part of the question. So I'm going to use trial 1. You can use any trial you want. The rate constant actually is constant. So if you want to just for funsies, I'm going to use trial 1. If you want to do trial 2 while I'm doing trial 1 and see if you get the same answer, that would be cool. So I'm going to take this information and I'm going to plug it into my rate law. So 1.2 times 10 to the negative third molar per second. That's equal to my rate constant, which is my unknown here, multiplied by the concentration of bromate squared, right? Don't forget to square it. I do have a 2 here for my exponents. We do need to square that concentration. Multiplied by my concentration of bromide. And I forgot my units. Don't forget your units. 0 molar squared. and my concentration for bromide, 0.10 molar. We need those. Our units on our rate constant are going to vary depending on what my rate law is. So do put those units in there so we can figure out the correct units when we do our problem. So I'm grabbing my calculator. Again, don't forget to square that 0.01. Sometimes like people will write down the 2, but then when they're doing the math, they'll forget to square it. So I'm actually going to type in 0.01 times 0.01. You can use your square button if you'd rather, times 0.1. Oop, I just subtracted it. And then 1.2 times 10 to the negative third divided by that. I get that my rate constant is equal to 120. I do need 2 significant digits in my answer, and remember that trailing zeros, if there's no decimal point, are not significant. So 120 is just 2 significant digits. So I'm good with this. And now we need to look at our units. So I'm going to do the units kind of separately on the side. So here I'm taking molar and I'm squaring it, and then I'm multiplying it by molar. So what I have on that side is molar cubed. I'm then dividing that into my molar per second. So I'm taking molar per second and I'm dividing it by molar cubed. Maybe it's easier to see if we do that whole invert and multiply. So if you remember fractions from when you learned to divide fractions back in grade school, I would take molar divided by seconds, and I'm going to multiply it by 1 over molar cubed. What's going to happen is this molar then is going to cancel out one of these, so this is going to become a 2. So my units are 1 over molar squared seconds. Often this is written, remember I said that if you have exponents on the bottom, it's the same as a negative exponent. So that's the same thing as a -2 seconds to the -1, which is probably the more common way to write the units on our race constant. You could leave it like this if you wanted, or you could write it like this. Either one's correct. With the negative exponents, though, is probably a little more common. Do be careful on units on these. It's almost a separate little algebra problem itself. So back to my answer, 120 molar to the -2 seconds to the -1. So that's my rate constant. We're still not done with the problem because we need to solve for our rate for trial 5, but we now have our rate constant to plug into our problem. So back to trial 5. I'm going to use my rate law again, and I'm now going to plug in those numbers. So this time we're solving for rate. That's my unknown. My rate constant, 120 molar to the -2 seconds to the -1, multiplied by my concentration of bromate, which is 0.04. We're going to square that, right, because it's second order with respect to bromate, multiplied by my concentration of bromide. I wanted a pen, which is 0.40. And that's raised to the first power. So grabbing my calculator again. Again, don't forget to square the 0.04. Hopefully you guys are typing these into your calculator also. It is very possible that I type something in wrong. I am not immune to calculator errors. So if you get something different than me and you're pretty sure that you did it right, please ask me, because it could be you. That's correct. Okay, so I got that my rate is equal to 0.0768. I only want 2 significant digits on this, So 0.77, and then my units, I dropped units on you guys again, I'm horrible. Molar squared, and this is molar. So this time, these 2 molar will cancel out 2 of those, and I'm going to be left with molar per second, which is going to be our units on our rate. It's always going to be, for us, molar per some unit time. The unit time in this case happens to be seconds. It should match, I didn't mean to scribble it out, it should match these units. So if it doesn't come out to that, you did goof up somewhere. And then if I look, is my answer kind of in the ballpark? If I got like 200 for my answer, these are all in terms of like a negative exponent, so I would kind of question it. This isn't. This is a negative exponent, right? If I wanted to put it in scientific notation, I would move it over 2 spots. 7.7 times 10 to the negative 2 molar per second. One more example for us. So this table, I'm going to move this down and write the problem first. So given the following reaction, and experimental data, we're going to do a few things. We're going to write the rate expression, determine the reaction rate for oxygen, let's say for oxygen disappearance, when the rate of nitrogen monoxide appearance is 0.024 molar per second. C, we're going to determine the rate law for the reaction. D, determine the initial rate for trial number 4. So that'll be in our table here, which I will blow up for us. So all sorts of stuff. You do need the equation. So our equation is 4 ammonia, NH3, and that's reacting with 5 oxygen to produce 4 nitrogen monoxide plus 6 water. So this is our reaction. And then our experimental data. Let me make this a little bigger for us. So what I really would like you to do is do this on your own. So please hit pause, go through this entire problem on your own. After you've done it, then hit play again and then work through it with me. You can check your work. You're gonna have to be able to do these on your own, so now is a really great chance for you to practice that. Alrighty, so hopefully you guys had a chance to work on it. So rate expression, that's the first part where we're going to look at changes in concentration over change in time. So my rate expression, and I'm gonna actually move this down and put the rate expression above it. So it's gonna be the word rate. And it doesn't matter the order that I put these in. I'm just gonna go left to right, but if you wanna mix them up, by all means, go for it. So change in concentration of NH3, ammonia, not ammonium, over the change in time. Since I have a coefficient of 4, I'm going to put that 4 in my denominator. Because it's a reactant, I'm going to put a negative sign in front of it because its concentration decreases over time. I'm going to do oxygen next. So change in oxygen concentration over change in time. It has a coefficient of 5, so that goes in the denominator. Again, it's a reactant, so it disappears, right? It goes away over time, so I'm going to put a negative sign in front of it. Change in concentration of nitrogen monoxide over change in time. I have a coefficient of 4, so that goes in the denominator. It's a product, so it appears, so it's a positive value. If you want to put the positive sign there, go for it. You don't have to, however. Change in concentration of water over change in time. I have a coefficient of 6, so 6 is going to go in my denominator. Again, it's a product, so it appears as time goes on, so it would be a positive value. If you wanted to write these instead of, like, for the first one putting the 4 on the bottom, you could do 1/4. If you prefer writing it that way, by all means, it's the same thing. So that's part A, that's my rate expression. Part B, determine the reaction rate for oxygen disappearance when the rate of nitrogen monoxide appearance is 0.024. And I'm going to use stoichiometry. This is the one where we could use either the rate laws or we could use stoichiometry. Sorry, not rate laws, the rate expression or stoichiometry. If you were going to use or did use the rate expression, sorry, I keep saying that wrong. The rate expression, right, what we just wrote in part A, you're going to use this part and this part because that's what we're solving for. What I'm going to do is I'm going to use my balanced equation and I'm going to use the coefficients in front of oxygen and nitrogen monoxide. So my rate of disappearance for NO is molar per second, and that's for NO. Looking at my balanced equation, there's 4 nitrogen monoxides for every 5 oxygen. So I'm grabbing my calculator, 0.024 multiplied by 5 divided by 4 comes out to 0.03. I do need 2 significant digits, right? Those coefficients are counting numbers, they're exact numbers, so they don't count for significant digits. 0.024 is 2 significant digits, so I do need 2 in my answer. My calculator is telling me 0.03, but remember, calculators don't do significant digits, right? We're smarter when it comes to significant digits than our calculators are. So you do need to add that 0, otherwise you will lose some points for sig figs. Molar per second. So that is part B. So C, determine the rate loss. This is where we're going to use our table. So this is where I'm going to look for trials where I'm varying one of my reactants, keeping the other constant. So if I look at trial 1 and 2, the concentration of ammonia is constant, but my concentration of oxygen is changing. So if I take 0.06 and divide it by 0.03, I am doubling my concentration, right? This is going up 2 times. If I look at this, and if you don't see it, by all means type it into your calculator. So take 0.0068, divide it by 0.0017, you get a 4. So it goes up 4 times. So for oxygen, what is my order? Yeah, hopefully you guys got second order for that, right? Again, if you don't see that, my rate is going up 4. So if we just think rate proportional to concentration raised to some power, what has to go in there, right? This is a 2. What's that exponent have to be? The reason I'm using proportional here instead of an equal sign, because the rate is equal to my rate constant times the concentration, and the constant isn't part of this. So it's not actually equal to that, but the constant doesn't change. Okay, 2 more trials. Let's look at trials, I guess 3 and trial 1. Let's erase the others here. So if I look at trial 3 and 1, right, oxygen's not changing, but my concentration of ammonia is. And if I look at these two, it's going up by a factor of 3. Again, if you don't see it, take 0.45 in your calculator, divide it by 0.15, see what you get. This one, if I take 0.0051, divide it by 0.0017, I get 3. So if I increase my concentration 3 times, my rate goes up 3 times. So what is my order with respect to ammonia? Good. Hopefully you guys got first order for that. So rate equal sign lowercase k. So this is my answer for part C. Determine the rate law. One part left, and that's to determine my rate for trial 4. So we do need to first solve for my rate constant. So I'm going to use trial 1. You could use 2 or 3. It really doesn't matter. So I have 0.0017 molar per second equal to K multiplied by 0.030. I wasn't going to forget units this time. Molar squared multiplied by 0.15 molar. And that's raised to the first power. So typing this into our calculator. Oops. Sorry, I got an error here. Let me do this again. So when I typed that in, I got that my rate constant is, it comes out to 12.5925, a whole bunch of other numbers. I do want 2 significant digits, so we're going to end up rounding that to 13. And then unit-wise, I'm actually going to have molar to the -2 again, seconds to the -1. Again, if you want to write it as 1 over molar squared seconds, by all means, it's the same thing. I'm now going to take that number, take my concentrations for trial 4, plug those into my rate law, solve for my rate. So my rate is going to be equal to 13 molar to the -2 seconds to the -1 multiplied by my concentration of oxygen squared multiplied by my concentration of ammonia raised to the first power. So getting my calculator again. And I got 0.028. I'm going to type this in one more time. Sorry, guys. When I did this earlier, I got a slightly different answer. So I want to make sure that I'm typing it incorrect. Typing it in correct, not typing it incorrect. Yeah, I get the same thing this time. So 0.028. And then the units do come out to be molar per second. So that would be our answer for part D. We could add one more part to this. I could ask what the overall reaction order is, because we didn't do that, right? We said it's second order with respect to oxygen, it's first order with respect to ammonia, and then it's third order overall, right? We add our exponents to get the overall order. So I have an exponent of 2 on oxygen, an exponent of 1 on ammonia. 2 plus 1 is 3. So overall, my reaction is third order.